In this video, we use thermodynamics to determine whether or not a given chemical reaction takes place. Consider a reaction in which 2 moles of A react with 1 mole of B to produce 2 moles of C. Its reaction product Q depends on the activities of products and reactants, as well as on their stoichiometric coefficients. In this particular case, Q equals activity of C to the power 2 divided by the product of activity of A to the power 2 and activity of B to the power 1. In what follows, activities may be replaced by partial pressures for gases and concentrations for dilute solutions. Also, activities are equal to 1 for solids and for solvents in dilute solutions, as water in dilute aqueous solutions. For each chemical reaction, there is a specific value of the reaction product Q, which corresponds to chemical equilibrium. This value is noted K and can be determined experimentally or looked up in thermodynamic tables. The free energy change, delta G, of a chemical reaction can be subdivided in a first part relating to the compounds in their pure state, delta G0, and the second part accounting for the mixing of these compounds, plus RT ln Q, giving delta G equals delta G0 plus RT ln Q. At equilibrium, delta G is 0 and Q is replaced by K. So, delta G0 equals minus RT ln K. This establishes a link between the equilibrium constant K and the free energy, specifically the standard free energy of reaction delta G0. The value of the equilibrium constant, or that of delta G0, tells us in which direction a reaction would go if all reactants and products were initially having an activity of 1. Specifically, if K is larger than 1, then delta G0 is negative, which tells us that the reaction is spontaneous in the forward direction and that it is displaced towards the products. One generally considers that all reactants are consumed if K is larger than 10 to the power 7. Conversely, if K is smaller than 1, then delta G0 is positive, which tells us that the reaction is not spontaneous in the forward direction and that it is displaced towards the reactants. One generally considers that no products form if K is smaller than 10 to the power minus 7. To consider more general cases where the activities of the reactants and the products are not all equal to 1, we look at the ratio of Q over K. Remember that Q is the reaction product obtained using the activities of the compounds as found in the system, while K is the specific value of Q at equilibrium. This means that Q over K is equal to 1 at equilibrium. Let us take the case of sodium chloride and water as an example. In a saturated solution, there would be a dynamic equilibrium in which the rates of dissolution and precipitation of sodium chloride would be equal. In this case, the amounts of dissolved and precipitated salt remain constant over time, and the solution is said to be saturated. If Q over K is not equal to 1, then the reaction is not at equilibrium. If Q over K is smaller than 1, the reaction will go from left to right and the solid will dissolve. If enough solid is present, dissolution will stop when equilibrium is reached. Otherwise, the solid will completely dissolve. Let us consider our example, and in particular the case of mixing water with a large amount of sodium chloride. The solid will dissolve to release sodium and chloride ions into solution until equilibrium concentrations are reached. Dissolution stops, and the excess sodium chloride remains as a solid. If Q over K is larger than 1, then the reaction would go from right to left to reach equilibrium. In our example of sodium chloride, it would mean that the solution is supersaturated and that sodium chloride would precipitate, reducing solution concentrations until equilibrium would be reached. Chemists make quantitative use of equilibrium constants to determine how and to what extent they can tweak reaction conditions to maximize their yields. Here, we consider the change of concentrations and relate their consequences to the qualitative principle of Le Chatelier. For more on this, please view the corresponding videos. Let us, for example, imagine that 3 moles of C are added to our mixture. Can you predict what will happen? Pause the video and think. By increasing the concentration of C, the value of Q increases. It becomes larger than K and must be reduced. For this, the system reacts by both decreasing the concentration of C and increasing the concentrations of A and B. From the Le Chatelier point of view, the system reacts to oppose the increase of concentration in C so that the reaction goes from right to left. In summary, we have seen that the free energy change of a chemical reaction can be divided in 2 parts, one defined by its pure compounds, delta G0, and one by their mixing, RT ln Q, where Q is a reaction product. Delta G0 can be looked up in tables and serves to determine K, or vice versa. Calculating Q from the concentrations available in solution and comparing the obtained value to K indicates if the system is at equilibrium, or, if not, in what direction the reaction should proceed. Moreover, reactions having a particularly low value of K produce very low reaction yields, while reactions with very high values of K have very high yields, giving complete or almost complete reactions.